Okay, so the first one here is kind of like a propane tank. It's a cylinder with a half sphere on each end of it. And we talked a little bit last class about dividing stuff up and putting it back together. We did that racetrack where we cut the ends off and put them back together to make full circles. Kind of the similar thing here. You're going to want to cut this off on the ends here so that you have a cylinder and two spheres. So for volume, you have this cylinder after we cut off the ends of it. Yeah, we'll give it a say. Is it back now? Yeah. Okay. So that cylinder is, the base is 30-inch diameter. You need to figure out the height. Well, if it's 100 inches overall, what is the radius of this sphere? 30-inch diameter, that's going to be a 15-inch radius, correct? So if that's a 15-inch radius, that means there's 15 inches here and 15 inches here. What's left over in the middle here? 70 inches. So that cylinder is 70 inches tall. So the area of the base is pi times 15 squared. Very good. So 3.14 times 15 squared. 706.5 we're going to get. That's going to be square inches. So my volume is going to be the 706.5 square inches times 70 inches. That sounds right. Yep, 49,455. That is cubic inches. For surface area, do we need the area of the bases? Well, if we look at our object up here, are the bases part of the exposed surface? No, the bases are covered with those spheres. So normally for surface area, we would need the area of both bases. And we have already figured that out. That is the 706.5 square inches. But since the bases in this example are covered by those half spheres, we don't need the area of the bases in our final area. All we need is the lateral area. This part here is our lateral area. So let's figure that out. To do the lateral area, we need the perimeter of our base, which is pi times 30 inches, otherwise known as 94.2 inches. So then our lateral area is the perimeter of the base, 94.2 inches, times that height of 70 inches. That sounds right. Yep, 65.94 square inches. So that is the surface area that matters from the cylinder. Like I said, we didn't do the area of the base because the bases were covered. Now we have to do the volume of the sphere. I should probably cut it this way since that's the way the sphere is cut in this problem. And that sphere has a radius of 15, as we said. So we're going to find the volume. Volume for a sphere is 4/3 times pi times radius cubed. So 4 divided by 3 times 3.14 times 15 to the power of 3. 14,130. That's inches cubed. So we have our components right there for volume. We add the two of these together to get our total volume. It is going to be 63,585 cubic inches. Anybody get that for their volume? Any questions on where it came from? Okay, to finish off our surface area, then we need the surface area of the sphere, which is just 4 times pi times that radius squared. So 4 times 3.14 times 15 squared. Yep. 2826 inches squared. And that's going to combine with our lateral area from the cylinder, which is going to combine. So this is the volume. Our surface area, if we add those together, is going to be 84.20. You are correct. It is 94.20. Square inches. Any questions? Are we having fun yet? No.
I was getting frustrated doing homework yesterday. I kept punching in all these numbers and I thought I was way off. And I put them in anyway and I got it right. I don't know.
Yeah.
But I got it right.
When it comes to areas and volumes, it does come down to a lot of formulas. So now here, and they said these two problems, the biggest thing is figure out how to pick it apart into pieces that we know how to find. This one here, number 2. Number 2 comes down to 2 pieces. We have a box. There's 24 by 24 by 12. That's the lower part. And we have a pyramid. What's the sides of the pyramid here going to be?
24.
That's 24 by 24. And you're given the height is 16. So we have to find the volume. Now again, for surface area, they're going to be pieces we need to subtract out. Let's start with the box over here. For volume, do a little adjustment here. So for volume, we're going to find the area of the base first. The area of the base is just the 24 by 24, which is 576 square feet, correct? So then the volume from that, take the area of that base, the 5,000 or 576. I don't know where the 1,000 came from. Square feet times the height of 12 feet, which gives us 6,912 cubic feet. So that is the volume for the box part, right here. Let's jump over and find the volume for our pyramid as soon as our system comes back. There we go. For the volume of our pyramid, we also need the area of the base. Well, the area of that base is the same as the area of the base for the box. It's 24 by 24, so it's 576 square feet. Its volume is then going to be that 576 square feet times that height, the 16 feet. But what do we have to do to it? Divide by 3, which comes out to be 3,072 cubic feet. So those two numbers right there add up to make our total volume of 9,900. Come on. And 84 cubic feet. For surface area, for our box, we have the area of our base is 576 square feet. Normally on a box, we would add in the bases twice, wouldn't we? Because you got the one on bottom here, then there's one on top. But for this one, the top is covered by the pyramid, isn't it? So we're only going to put it in once. So we have that portion. Now we need to do the lateral area. For the lateral area, what's the first thing we need to know? Perimeter of the base. Which is 24 plus 24 plus 24 plus 24. Or 190, no, 92, right? 96. Wow, I'm off today. 96 feet is the perimeter of the base. For a lateral area, there's 96 feet times the height of 12 feet, which is 1,152 square feet. So that tells us our total surface area from that portion of it, at least, is 576 plus 1152, which is going to be 1728. Now for our pyramid. We know the area of the base is 576, but is that part of the surface area on this one? No, normally it would be for a pyramid, but that base of that pyramid is sitting on top of the box. It's not exposed. All that is exposed is the lateral area, these triangles. To find that lateral area, we need to know not only the perimeter of the base, which we already found, which is 96. The perimeter of the base is still 96. We need to know that slant height. So to find that slant, we got that this is 16 feet here. What's this down here? That's 12, half of the 24. So 16 squared plus 12 squared. 16 squared is 256. 12 squared is 144. That adds up to 400. That equals our C squared or slant squared, however you want to look at it. Square root that. 20 equals our slant. So that means is our lateral area is the perimeter of the base, 96 feet, times the slant height of 20 feet. And since it forms triangles, it's divided by 2, which is 960 square feet. So we add those two together, the 1728 and the 960, to get a total of 2688 square feet. Hopefully that comes back for you. Yep.
So that is the 960 plus the 1152.
Yep. Or no, not the 1152, sorry, the 1728. Because the 1152 is just part of it. We had to add the 576 to the 1152 to get the whole surface area from the box. We're assuming we're doing the bottom of the box. If that were a house or something like that, we wouldn't do the bottom of the box either, but we didn't specify what it was. Any other questions? Volumes and surface areas, I'll be nice to you on it. As you can see with these two examples, I can really do a lot of damage if I want to. We will stick mostly on the test, at least when we do our test here the end of next week. We will stick, not the end of next week, the end of 2 weeks, 2 weeks from today, basically. We will stick to just straight a box, a cylinder, a pyramid, a cone, or that triangular shaped prism. Yeah, I won't put like 2 or 3 pieces together like I did in these 2 examples. Yeah. They will be straightforward shapes rather than ones you have to split apart like these. But in real life, this is what you have to do. I mean, you start doing calculations for BTUs on a furnace. You have to calculate the volume of the interior of a house and stuff like that. Okay, well, it's time to tackle some new stuff. That's what y'all wanted to hear? What we're going to do here right now, we've actually seen a little bit before. When we have a figure, a shape, that's taken from another shape but just either enlarged or reduced, do you remember what that's called? It's called similar figures. And most of the time we're working with triangles. So here, I actually did it in front of you so you could see that that smaller triangle is just a reduction of the larger triangle. So let's say that in this larger triangle here, we have sides of 18 feet and 30 feet here. And this one is 6 feet and 10 feet here. If this side is 24 feet, how would I find the length of side X there? My missing side. Well, I really should mark out this angle and this angle are the same. And this angle and this angle are the same. Oop, that is not what I wanted to do. There we go. And this angle are the same. The reason being is the definition of similar figures, or part of the definition of similar figures, is all the angles, all corresponding angles. Are equal. By corresponding angles, that means the angles that are in the same spot before and or after the enlargement or the reduction. And the reason I needed to mark those angles here is so you know that it wasn't flipped or rotated or anything like that. So we now know that the 18, the side for the 18 corresponds to what side from the small triangle? The 6. And the 30 corresponds to what side from the small triangle? The 10. So then the 24 corresponds with X. Okay, and we need that to start out to set this up correctly. So when we go to set up this problem, it's going to be a proportion because similar triangles, well, part of the rest of the definition is the sides are proportional. So when we look at this, we need to find one pair of sides, one pair of corresponding sides where we know both lengths. In other words, we know the before length and the after length. Well, we actually have two pairs of those. We've got the yellow pair here, the 18 and the 6. And I've got the orange pair, the 30 and the 10. I'll use the 18 and the 6. That proportion, that ratio of sides between the original triangle and the reduced triangle should be the same. For example, if I use the 30 and the 10, that should give me equal ratios. How do I test to see if those ratios are equal? I use the cross products. As soon as it comes back, we'll look at those cross products. So our cross products it's gone again. Okay. There we go. So our cross products, still can't see it? Well, let's pause it here. So we have those two ratios. To tell if they're equal, I mentioned that word cross product. What the cross products are, we've talked about cross multiplying and dividing to find the missing piece in a proportion. Well, cross products are the same thing, only you're going to cross multiply in both directions. So here we're going to multiply 6 times 30 is 180. 18 times 10 is 180. When those two cross products are equal, that means the two ratios are equal. So that ratio of 18 to 6 is equal to the ratio of 30 to 10. That ratio then has to remain equal for the third side. Now, I didn't have to test this out. By telling you that those triangles are similar, it's implied that these two ratios will be equal. But I just did that to show you that they will be equal. So I'm going to go back using that 18 to 6 ratio for this side related to this side. Now I want to find out what X is equal to. Where is X going to go here, on top or bottom? Does it relate to the 18 or the 6? The 6. It's from the same triangle as the 6. So X goes on bottom with the 6. What's going to go above it has to be the corresponding side then from the other triangle, which is the 24 that we have in blue there. And now we go back to what we were doing before when we were finding missing parts of a proportion, and that is cross multiply and divide. So 6 times 24 is 144, divided by 18 is 8. So x is 8. So this here has to be 8 feet in length. What do you think? Still better than a sharp stick in the eye? Somewhat. Now, it doesn't stay that simple. You knew it once. We can have a situation like this, where this here might be 24 feet. And let's say this side up here is 48 feet. We'll call this side X. I'm going to tell you that this angle here and this angle here are equal, and these two are equal. Now, before I put stuff into the other one and the other triangle, label any sides, I said up above that all the angles have to be equal. Why did I only mark 2 of the 3 angles? Exactly, because the angles of a triangle must add up to 180. If 2 of them are equal, what's left over has to be the third one. The third one has to be equal. So let's say that this over here is 10 feet long. And let's put this one up here we're going to call Y. And let's see here. You ever have one of those days where your mind just blanks out on you? I'm having one of those for some reason. I believe this one's going to be 22.5 feet. It'll work. The numbers just may not be pretty. So again, I often will go through and mark which ones correspond. So like, what side from the other triangle corresponds to the 48? The Y. Very good. Because it's between the 2 marked angles, right? That's not supposed to look like a right angle there, by the way. That's just an arc. What side from the other triangle corresponds with the 24? The 10. And which one corresponds with the X? 22.5. Okay. So now, do we have any sides where we know the corresponding side from both triangles? 24 and the 10. Very good. So we know we've got that ratio, 24 over 10. Could we have done 10 over 24? We sure could. Yeah. It doesn't matter which one we put on top, 24 over 10 or 10 over 24. It will work out the same. It just means that when we do the other side, we have to make sure we match them up the same. So let's say we're going to try to find side X first. Is X going to go on top or bottom? It must go with the 24 because it's from the same triangle as the 24. So wherever the 24 is, the X has to go. So if we'd flipped it over and the 24 was on bottom, X would go on bottom. Since our 24 is on top, X goes on top. What has to go beneath the X? Yes, its corresponding side from the other triangle is 22.5. So now we cross multiply and divide, and we get that X has to be, well, 24 times 22.5 divided by 10. 22.5 times 24 is 540. Divided by 10 is So this side right here, 54 feet. Now we want to find side Y. You guys tell me what to do. We'll use the 24/10 again. And then, there we go. The Y has to go on bottom because it's from the same triangle as the 10. 48 is going to go above it. And now we're going to cross multiply. This time it's going to be 10 times 48, which is 480, divided by 24, which is 20. So Y, it's not inches, it's feet. It's 20 feet. Any questions? Have we had any flickers in the content screens on the other ends in the last, since we rebooted? It's been good. I think we're good, Brett. Because it was going way more often than that before. I'm hoping that's what it was. Thank you. Okay. Why would we care about stuff like this? How is this really useful to us? Well, I think I did an example like this before, but let's do it again. You've watched way too much public television. A happy little tree. Yeah. He's just frustrating to watch because even with him breaking it down step by step, making it look so easy, I still can't do it. So let's add some excitement to this. We'll say that that's my house and my happy little tree. And it's a bright sunny day, that's for sure. And I am looking at cut down my tree. And that's red as the chainsaw, it's not me bleeding. Yeah. I want to know that when this tree hits the ground, is it going to hit my house? So what I need to be able to figure out is, well, we're going to cut it off we're going to claim that we're going to cut it at exactly the bottom of the tree down here. Okay? We're going to get that stump as close to the ground as we can. Well, we have the sun shining up here, creating a shadow for the tree. Pretend that looks like a tree shadow. And I can use that by taking something else. Let's say that over here I have a post that's exactly 8 feet tall. And its shadow from the sun is 10 feet. So I come back over here and I'm going to measure from the center of my tree to be safe to the end of that shadow. And I find that that shadow is 65 feet long. How tall is my tree? Well, if I let H or X or whatever be the height of my tree. It's H over 8, or I could have done 65 over 10, however I wanted to do it, equals 65, because 65 comes from the tree, H came from the tree, 10 comes from my post, the 8 came from my post. So now it's going to be 8 times 65, which is going to be 520, right? Divided by the 10, 52 feet of height. So my tree is 52 feet tall. Now, I didn't tell you how far it is to the house, but I'm pretty sure it's not going to reach it. How do I know that? Well, there's a 65-foot shadow between the tree and the house. I'm pretty sure it's more than 65 feet. Let's say I have a rectangle here that is 3 inches by 8 inches. And I am going to blow that rectangle up to make it 9 inches by 24 inches. What is the ratio of lengths between those two rectangles? Well, 3 inches became 9 inches, or 8 inches became 24 inches. Either one, that reduces to 1 to 3, or you could have done 3 to 1, the other way around, right? What is the area of this triangle? Or this rectangle? 24. 3 times 8 is 24 square inches. What's the area of this rectangle?
Mm.
216 square inches. My ratio of areas is 24 to 216. Both of those can be reduced by what? 2 would give me 12 over 108. Still be reduced by 4. Let's do 4. Gives me 3 over 27. And still be reduced by 3. 1 over 9. So the ratio of lengths was 1 to 3. The ratio of areas was 1 to 9. What if I take a circle with a radius of, oh, let's say that radius is 4 inches. And I enlarge it to make a circle with a radius of 8 inches. What is my ratio of lengths there? That went from 4 to 8, right? Yeah, so 1 to 2, very good. My ratio of lengths. My areas, this one here is pi times 4 squared, otherwise 50.24 inches squared. This one is pi times 8 squared, 200.96. My ratio of areas, if I put 50.24 over 200.96, reducing that's going to be kind of ugly, but both of them can be divided by 50.24. Gives me a 1 to 4 ratio. Are we seeing a relationship between the ratio of lengths and the ratio of areas in each of these? Here I had a ratio of lengths of 1/3, ratio of areas is 1 to 9. Here I had a ratio of lengths of 1 to 2, ratio of areas is 1 to 4. Are you seeing any relationship there? They are both divisible by the same number. In fact, they're both divisible by whatever this number is on the ratio of lengths. What is 3 squared? 9. Down here, this is a 2, right? What is 2 squared? 4. The ratio of areas is always the ratio of lengths squared. Now that doesn't matter whether it's a simple flat area or if it's a surface area. So where this is useful is if I have figures that are weird shaped like this. Let's get back here. Yeah, I know, you're gonna have fun drawing that in your notes. And let's say that I have the first one here, that I know this straight edge here is 8 feet. And the area of the whole thing is 200 square feet. And I go over here, and this has been reduced to 6 feet, and I want to find the area. Well, the ratio of lengths is what? Either 8 to 6 or 6 over 8, one of the two. Both of those can be divided by 2, so it's giving me a 4 to 3 ratio of lengths. For my ratio of areas, I am going to take that ratio of lengths there, 4 over 3, and I'm going to do what to it? I'm going to square it. What is 4 squared? 16. What's 3 squared? 9. That is what I am going to now set equal to the areas. The 200 square feet goes with which one? The 16 or the 9? That goes with the bigger figure, so it goes with the 16. So that 200 square feet, we're going to cross multiply and divide. 9 times 200 is 1,800. Divided by 16 is 112.5 or something like that. Is it? I don't trust my math here. 9 times 200. 112.5. I was right. So it's 112.5 square feet. So you can find missing areas if you know the ratio of lengths. Come on. I'm going to have to get used to doing everything with the mouse and not have my keyboard exposed. Yes, I am trying to do something artistic, which means, well, you have to be patient with me. Now I'm going to assume it's going to take a second for you guys to draw those in your notes or something similar to it. Yeah, you're going to need them in your notes. What we have here is a three-dimensional object. And the height of this first one here is 10 inches. The height of this one over here is 15 inches. The smaller one here has a surface area of 210 inches squared. Let's find the surface area of the other one. What's my ratio of lengths? 10 to 15, which can reduce to what? Both divided by 5, so it's a 2 to 3 ratio. Now, surface area is just an area. So I'm going to be finding my ratio of areas. And I'm going to find that by taking the 2/3 and doing what to it? Squaring it. What's 2 squared? 4. What's 3 squared? 9. What's going to go on the other side of this? 210 goes with the smaller one. That would be the 4. So 9 times 210 divided by 4. Was that 472.5, I believe? So that is the surface area of that second object. So as I said, whether it's a flat area or a surface area, that works out the same. Now let's add some excitement to this. Let's say that you are told the volume of this is 720 cubic inches. How could we use that to find the volume of this other one? Well, over here, our ratio of lengths is still 2 to 3. To find the ratio of areas, we took that ratio of lengths and we squared it. What do you think we're going to do to find the ratio of volumes? Cube it. What is 2 cubed? Is 8. 2 times 2 times 2 makes 8. What is 3 cubed? 27. 3 times 3 times 3 is 27. What goes on the other side? 720 goes on top. And we are going to cross multiply. 27 times 720 divided by 8. 2430, not 1530. $2,430. So this is 2,430 cubic inches of volume. What do you think? Okay, well, we're going to leave that at that. And we're going to start talking about our stuff for the second segment of class here. And that is graphing. Now, I'm talking about graphing here, not in terms of making like bar graphs and pie graphs and that stuff. Those are statistical graphs or data graphs. So that's the bar graph. and the pie graph and stuff like that, line graphs and all that good stuff. That's not what we're going to be looking at here. We will look at those sometime in the next week and a half, but that's not our focus today. What we're focusing at today is we want to graph paired data. In other words, we're looking at numbers that are linked together somehow. And to explore that, let's look at graphing, representing a number on a graph of any sort. So let's say representing a number graphically. To represent a single number graphically, we've used a tool already called a number line. And a number line is a graph. So if I want to represent the number 6, there are a couple of ways I can do it. Now, the one we talked about when we were doing negatives, we talked about vectors in a number line. You start at 0 and you go to 6 with that vector. That is what we need to use for operating with our numbers. If we're going to do operations with them, we're going to do anything with them, that vector works best. But if we're just like showing the number 6, that vector can get kind of crowded. If we're going to show a lot of numbers, there's going to be a lot of vectors there and they get kind of crowded. So an alternative way that we discussed before that didn't work well for our operations, but it does work well if I'm just showing the value, is just putting a dot at 6. That dot on the 6 represents the value 6. And I can put other dots. Of course, this dot represents what value? -2. And this dot represents 11. And this dot represents -5. And this one represents 0. Right? But we said we want to look at paired data or linked numbers. So let's say we want to look at numbers that are linked together. Like let's say we want to say 6 and 2 are linked together. Well, we've got the 6 up here. I suppose we could put the 2 up here and then like connect them or somehow. But just like the vectors would get pretty cluttered, those little connecting arches would get pretty cluttered. In fact, what we want to work with is something called an ordered pair. So not only are the numbers linked together and connected, the order matters. An ordered pair is written like that, 6, 2, and it's in parentheses. And 6, 2 is different from 2, 6. Which one comes first does matter. So up here, I would have to somehow show that the 6 came before the 2. Whether I put an arrow there like that or something to indicate 6 and then 2. Well, this would get very, very sloppy if I had to do arrows between the points to connect. It's not going to work. Well, a couple thousand years ago, like I said, this all happened before television when people actually had free time on their hands. Can you imagine if they had television 3,000 years ago, how much stuff we wouldn't have right now? You guys are probably thinking, yeah, a lot of this math crap we got to learn. But anyway, a man by the name of Rene Descartes. He was French, yes. Came up with a way of doing this. Really what happened back then, there was several ages throughout history. You know, you've heard of the Dark Ages and the Renaissance and stuff like that. The Dark Ages was where I'm not sure how familiar you are with the government structure in Europe. Now there's actually countries, and there were countries then too, but it was much more loosely formed because you couldn't really communicate across great distances back then. Most of the power was held locally. So there would be a castle with some sort of a nobility, a duke or whatever, and the land within the immediate area of that castle, he would protect those people from anybody else trying to invade them. And then those people would basically give their part of their money or part of their crops to that king, and or that not that king, but that nobleman, whether it was a duke or whatever it was. And that's how that noble person survived. And that noble person then used that food, would feed, some soldiers or whatever to protect that land. And then on the bigger scale, there was, I don't know what the next step up from duke was. They would have a castle somewhere, and then each of those little, dukes or whatever would send a little bit up to that person so that they could have an army, so that if they were invaded by someone larger, they would help protect all those smaller places if they got overwhelmed. And then there was the king somewhere eventually on top that everybody sent stuff up to that had an army. Bless you. But in the Dark Ages, they did a lot of fighting. What's that? No, they did a lot of fighting back then, and they, if they had a dispute over land or whatever, they would fight whoever won took that piece of land, or they just fought to prove who was stronger, whether they took any land or not. Well, as they went into the Renaissance period, rather than fight, they decided all we're really doing with this fighting is killing our people and losing people, and we have less people to do the work that we need, and to basically it's costing them money, and they're becoming poorer and poorer. So they decided, hey, let's stop draining our resources and let's compete somewhere else. So they started competing over knowledge. Each of those noble people would bring in mathematicians and philosophers and whatever. And they would see, and basically it was, haha, we know something you don't know. One of our guys came up with something and you guys don't know it yet. And that's why there was that huge rush of knowledge, because they started competing over knowledge rather than over military superiority. And Descartes was part of that. These great intellectuals were actually given a tremendous amount of power. They were given the ability, they took in kids to train and teach so that those kids could learn and they could grow up to increase the knowledge base and whatever. It was really the beginning of the educational system, outside of just working beside your family and learning the family trade. So what Descartes came up with is a system where we're going to take that number line, and we're going to keep it just like it is as a regular number line. Positives on the right, negatives on the left, just like any other number line. And we're going to allow that to represent the first number of the pair. And then we're going to take a second number line. But instead of making that one horizontal, we're going to make that one vertical. With the positives going up and the negatives going down. And that one is going to be used to represent the second number in the pair. Now, we have most likely been taught that this is what's called the x-axis, that first number line. And the second number line going up and down is called the y-axis. And that's because x and y are the variables that are most often used for those. Must have been going by with a vacuum or something. X and y are the variables that are most often used for those things. We often list that ordered pair as x comma y like that. But it's not always x and y. In fact, quite often it's t instead of x if we're doing time or whatever. So the more appropriate labeling is the independent axis and the dependent axis. What that means is most of the time, this is kind of a crossover between the geometric graphing and the data graphing. Most of the time, the value that's being put on this horizontal axis, what we call the x-axis, most of the time that is a variable that's allowed to change however it wants to. Like if it's time is going to move on whether we want it to or not, right? Or if we're comparing height and weight, you would let the height be the x-axis, the independent axis, because the weight is most likely being affected by your height. You can get heavier without getting taller, but it's really tough to get taller without getting heavier, if that makes sense. So the dependent axis up here is the one that is affected by the other one. It's not totally controlled by it, but it is affected by it. Like one of the classic experiments was the number of times a cricket chirps in a minute compared to the temperature. And if you take a cricket and you warm it up, it'll actually chirp more often, or if you cool it down, it'll chirp less often. So the temperature would be the independent axis because you're changing the temperature, but the number of times it chirps would be the dependent axis because the temperature determines how rapidly it chirps. So let's go back to that point 6, 2. 6 would go on the independent or the x-axis. That would be like right here. The 2 would go on the dependent or the y-axis right here. How do I represent the two of them together? I trace them out to where they intersect out there. That red point represents 6, 2. Represents both numbers at once. Because its shadow on the x-axis is at 6, and its shadow on the y-axis is at 2. If you, let's plot some points here and see if we can name them. What's this point right here going to be? 1, 4, 1, 4. Very good. How about that point? -5, 3. Very good. How about that one? 2, -4. Yes. How about that one? -3, -5. Good. How about that one? -2, 0. We got to have both points. Because that would be 0 here if we trace it over, right? It's at -2 this way and 0 that way. How about this one? 4, 0. Good. How about this point right here? 0, 3. We trace it down, it's at 0. We trace it over, it's at 3. It's on the axis. Or this one here. 0, -4. Good. If I traced it up, it hits 0. It's on the -4 on the vertical one. This coordinate system is used for graphing points and data like this. It is also used in CNC a lot. You're actually going to throw in a Z variable, a third directional variable. It can be used in mapping. It can be used in laying out job sites and construction. It can be used in sewing for locating points of corners of fabric and pieces of your pattern or whatever. Anything that can be laid out in a blueprint or a design is often laid out with this coordinate system. It is time for our break, so let's go do that. It is 10:18. Let's come in at 10:22.